Number 4. Answer the following questions about the solubility. Okay, so the solubility is how much of it's going to dissolve of calcium hydroxide. And the KSP of calcium hydroxide is 1.3 times 10 to the negative 6. Okay, now big K means what? Equilibrium. That's my equilibrium constant. So there's two things that you need to start thinking about when you see a big K. One, you need to start thinking products over reactants. Okay, and 2, you need to start thinking there's a possibility I may have to do a Rice table. All right, now it's not a definite you're going to have to do one, but there's a possibility. So anytime I see big K, I need to start thinking about those two things. Okay, if it's a short problem like this, where I don't see any delta G's or anything like that. Now I also need to start thinking about it in terms of favorability. Okay, now this K is less than 1, so I know this isn't going to be what? Thermodynamically favorable. It's going to be thermodynamically unfavorable. So those are just some things that should start flashing through your head when you see big K. All right? So A says write a balanced chemical equation for the dissolution of calcium hydroxide in pure water. So what they're saying for this is, what does calcium hydroxide dissociate into when I put it in water? What's it going to dissociate into? Thank you. Ca2 positive and what?
OH.
How many OH negatives?
2.
2. And that's plus 1. We can handle that, right? Right. B says calculate the molar solubility. So how much of it's going to dissolve. So how much of calcium hydroxide is going to dissolve in 1.10 molar calcium nitrate. Okay? Now, calcium nitrate. What do I know about nitrates? They're completely soluble. So this is going to completely dissociate into Ca2 positive plus 2 NO3 negative. Okay? Now, do I care about the NO3 negative? No, it has nothing to do with my calcium hydroxide. So it's a spectator ion. Don't really care about it. Do I care about the concentration of the Ca2 positive from that? Yes. What is my concentration of Ca2 positive going to be that I get from that? 0.10 molar, right? Because it completely dissociates. I only get one of those, so it's 0.10 molar. Now, if I cared about the nitrate, what would be the concentration of the nitrate? 0.2 molar, right? Do we see that? Okay. So I want to know how much of my calcium hydroxide is going to dissolve. So essentially, I'm solving for X at equilibrium. Okay? Now, why does it matter that it's at equilibrium? Because at equilibrium is where it's going to stop what? Reacting. Because the forward rate is equal to the reverse rate at equilibrium, right? So once I get it to equilibrium, I know that's when it stopped dissolving. Or it's going back and forth at the same rate, so that's the maximum amount that can dissolve, right? Right. So that means I'm going to need to set up a Rice table. So we already wrote our balanced equation. CaOH2 that's solid makes Ca2 positive plus 2OH negative. Right? Right. Then we have our initial, our change, and our equilibrium value. Now what am I going to cross out and not care about in this equation? Why do I not care about this one? Because it's a solid. Who is not included in equilibrium expressions? Solids and liquids. All right. What's my initial concentration of Ca2 positive? 0.10 molar. Why do I have an initial concentration of Ca2 positive? Because I what?
Because if you have...
Because I put it in a what? Calcium nitrate solution, so I'm already starting with some Ca2 positive. Do we see that?
Yes.
Okay. Now, how much of the OH negative am I starting with? 0, right? Do I have any OH negative in that calcium nitrate solution? No. So I'm starting with 0 of that. Does this make sense? We see that? All right. So my change, what's going to happen on the product side? plus x.
Yeah.
And what's going to happen here?
Plus 2x.
Plus 2x. Now, let's pretend for a second I did have something on my reactant side. It wasn't a solid. What would happen on the reactant side? Minus x, right? Is this coming back to us? All right, so at equilibrium, this would be 0.10 plus x, and this would be 2x. So now our rice table's set up.
The only way that it's going to be minus x on this side is if you start with the products. Right?
Would be if they were asking me to do the reverse reaction. And I don't think they'll do that to you. I really don't. All right, so next, what I like you to do is write your expression first. If you'll write your expression first, it will keep you from messing up your numbers. Okay? So what is my expression going to be? KSP is equal to what?
Products over reactants.
So the concentration of Ca2 positive times the concentration of OH negative squared. Okay? Am I going to have a denominator in this? No. Why? Because my reactant is a solid, so it doesn't get included. So now let's put the numbers in. Did they give me a KSP value? Yes. What is my KSP value? So 1.3 times 10 to the negative 6 is equal to, what goes in my Ca2 positive spot?
0 plus x.
Plus x. What goes in my OH negative spot? 2x, and then I'm going to square it. That would give you plus 1 point if you got that far at least. Okay?
So just write something down.
So if you got up to the setup, you're good. You got a point. So now I've got to solve for x so I know the molar solubility. Now notice, I'm going to neglect this x. Why am I going to neglect this x?
Because it's so small.
Okay? Because it's so small, and if I kept the x there, I would need the what? What would I need to use to solve this problem? The quadratic formula. Do they ask us to do that on the AP exam? No. Okay? So no, we neglect that x. So now I've got 1.3 times 10 to the negative 6 is equal to 0.10 times, what's 2 squared? 4. What's x squared? X squared. So now can I solve for this? Yes.
You sure
So
can.
1.3 times 10 to the negative 6 is equal to 0.4 x squared. So then I'm going to divide by 0.4. And then I'm going to do what? Take the square root. All right. How many sig figs do I need?
Look like 2.
2. I need 2. Remember? And 1.3, I've only got 2, so I need 2 sig figs. What's my answer going to be? Anybody going to give me an answer? What'd you get, Hope?
Got like 0.0018.
And what's my units here for x? Because we don't leave naked numbers in chemistry unless it's big K. Huh? M. Plus 1 for your answer. Okay. C. If you don't get this, I'm going to be angry with you, like angry face. All right? In the box below, complete a particle representation diagram that includes 4 water molecules, so they tell you how many they want, with proper orientation around the Ca2 positive ion. Represent your water molecules as Mickey Mouse, because it looks like Mickey Mouse to me. Okay? So, how are we going to draw this around the Ca2 positive?
Oxygen.
With the oxygen what?
Towards the CA.
With the oxygen pointing towards the Ca2 positive. Why do I want oxygen to point towards the Ca2 positive? Because that's the negative end. So where's oxygen at?
A large one.
The large one, that's oxygen. And then these are your hydrogens. Okay? So I'm going to draw it like this. And I get +1. There's Jeb's point right there on the AP
Really
exam.
is.
Okay.
Hey, I got a point though. There's people that don't worse than that. Yeah, they did.
They were also
They did. You're right. Terry, did you get anything on the response? You got one. No, we all at least got one.
All right, let's go to 5. All right. Number 5, blue food coloring can be oxidized by household bleach, which contains OCl negative to form colorless products as represented by the equation above. Okay, so what do we know bleach does? Takes away color. And how did they tell us it does it? Oxidizing. Okay? Everybody got that sentence. We understand it. A student uses a spectrophotometer set at a wavelength of 635 nanometers to study the absorbance of the food coloring over time during the bleaching process. Okay? So I take blue food coloring, mix it with bleach, put it in the spectrophotometer. I can't say that word, okay? So I put it in there. Now, I'm sending 635 nanometers of wavelength through there. I'll give you a hint. That's the wavelength of blue light. So I'm sending it through there. So as long as there's blue food coloring in there, what should the wavelength do? It should be absorbed into the food coloring, right? And as the bleach takes away that blue food coloring, the wavelength should eventually just what? Pass straight through as it becomes colorless, right? So that's when we would say the absorbance was 0 when it passed straight through, correct? Does everybody understand that? So when there's a lot of blue food coloring in there, it's going to absorb all of it. As it oxidizes and forms colorless, the absorbance is going to go to 0 because the light passes through. We did this lab, but I don't think you probably remember it, so now we're going back to it. Okay, except we did it with grape Kool-Aid. Okay? All right. In the study, bleach is present in large excess so that the concentration of OCl negative is essentially constant throughout the reaction. The student used data from the study to generate the graphs below. So here we have absorbance versus time. We have the natural log of absorbance versus time. And we have the reciprocal, 1 over the absorbance versus time. Okay, now remember, this absorbance is helping me measure concentration, right? Higher the concentration, the more wavelength that's absorbed. When my blue food coloring goes to 0 concentration, it passes straight through. You still with me? You're still with me. So, remember we did the graphs as concentration versus time, the natural log of concentration versus time, and the reciprocal of concentration versus time. So you may see them as concentrations instead of absorbance on the AP exam. Okay? Same thing. Do we understand that? All right. Graphing absorbance versus time is graphing which order? How many different orders are there?
It's first, second, third, so.
No.
0.
0
No,
first
0
and second. Absorbance or concentration versus time would be 0. Natural log versus time would be first. And reciprocal versus time would be second. Because remember, they're in alphabetical order. Okay? Concentration, 0. Natural log, first. Reciprocal, second. It's in alphabetical order. Got that? Got that. So, you gave me a graph. What do I notice?
If you put 0 in the second 0.
What do we notice?
First is different.
How is first different?
It's great.
It's a straight line. So when A asked me, based on the graphs above, what is the order of the reaction with respect to the blue food coloring, I'm going to say
First.
first order. Why am I going to say first order?
Because it's great.
Because he gave me the straight line.
Heck yeah. 2 points.
How do you know? Like, you know what I'm saying? Like,
It's supposed to be straight across when it's 0. Is that how you know if it's like straight across? How do you know if like which
No.
one? Just pick the one that's
How do you know
straight.
which one?
You just pick the one that's straight. If it was this kind of question, they would give you the 3 graphs. Or they might have done something where they didn't even give you 0 or second. They just gave you this graph, and they expected you to know that since it's natural log, that it's a first order because it's a straight line. Either way, you're looking for which graph gives you the straight line. Whichever one gives you the straight line lets you know what order of the reaction it is. Does that make sense? Yeah, and in this one they gave you both. So if they would have given, like if this one, if the first graph would have been a straight line and these two would have been curved, then I would have said a 0 order. Okay? So you just look for the straight line. All right? Okay. B says the reaction is known to be first order with respect to bleach. So apparently it's first order with respect to bleach as well. In a second experiment, the student prepares solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near 0 too rapidly. What's happening? Why is it reaching an absorbance of 0? All the blue dye is gone because the bleach is what? Oxidizing it and taking it away. In order to correct the problem, the student proposes the following 3 possible modifications to the experiment. We can either increase the temperature, increase the concentration of the food coloring, or increase the concentration of the bleach. What do we want to do? We want to increase the concentration of the food coloring. +1. Okay. Why do we want to increase the concentration of the food coloring?
there's more that is oxidized, more stuff that's longer.
Excellent. Okay. If I increase the concentration of the food coloring, I'm abbreviating. You can abbreviate, but just don't do it on your AP exam. If you increase the concentration of your food coloring, it will require more time. We'll let my smart board catch up. More time for the bleach to oxidize the food color. Plus 1 point for your explanation. We can think through this one so far, right? Yes? Good. All right, C. In another experiment, a student wishes to study the oxidation of red food coloring with bleach. How would the student need to modify the original experimental procedure to determine the order of the reaction with respect to the red food coloring? Change the wavelength. Plus 1.
See, I like these because it's really common sense.
They are.
You can think through them.
This one was very common sense. I liked it too. I'm hoping they'll give y'all one like that on the exam. All right, number 6. I like number 6. Takes a little thinking, but I like number 6. Okay? You can do number 6. I need you to think with me, and you can handle number 6. Okay? Number 6, a student learns that ionic compounds have significant covalent character when a cation has a polarizing effect on a large anion. As a result, the student hypothesizes that salts composed of small cations and large anions would have relatively low melting points. A. Select 2 compounds from the table and explain how the data from those 2 compounds supports the student's hypothesis. Okay? What do you need to know before you can answer this question? Okay? First of all, I need to know cations are what? Positive. Anions are negative. And I need to know how to gauge their what? Size. Okay? Do I know a rule that could help me with the size of these anions and cations? Yes. Let's look at the 2 anions. What are the 2 anions they give me? Okay, guys. L-I-I. What's the cation in this? Li, which is Li positive. What's the anion in this? I. What are the 2 anions they give me in this chart? I and F. Thank you. Okay. Now, what do I notice about fluorine compared to iodine? Fluorine's way up top on the periodic table, iodine's down here. So what does that tell me about their sizes? Iodine has a much larger radius than fluorine, right? So can I choose 2 of these compounds on here to support what the student said, that if I have a small cation and a large anion, the melting point is lower? Yes. Okay. Prove it. What can I say to prove it? What 2 compounds do I need to choose, first of all? Li-I and Li-F plus 1. We just chose the correct 2 compounds.
Heck yeah.
Okay? Now, how does the data up there support what the student said? Remember, they didn't ask you if the student hypothesis was correct. It's correct. Okay? They asked you to support it. Explain it. How can I support it and explain it?
How'd you know it was Li? How'd you know that? How'd you know it was the lithium?
You could have used these 2 if you wanted to. You could have. That's fine.
So you really just have to choose 2.
Yeah, it did. You either needed to choose these 2 together or these 2 together. Or technically, you could have chosen these 2 together. Yeah, you just had to choose 2.
So it really doesn't matter.
All right. You just have to make sure that your explanation supports them. Okay? So, how can I use this and explain what the student said?
I has a larger radii than F, and it has a lower melting.
Okay. I negative has a larger radius than F negative. Do we all agree with that?
Yes.
Yes. And what do we notice about the melting point of Lii compared to Lif? It's smaller. And Lii has a much smaller, has a much lower, I guess, instead of smaller. Melting point. Plus 1 for your explanation matching. So you see, I could have done that with Ki and Lif too. I is greater than F negative, lower melting point. I could have done it with those 2. Do you see what I'm saying?
Why would you include the melting point? I'm not.
Okay, because this says that the student says that salts composed of a small cation and a large anion should have a relatively low melting point. Huh?
I didn't see the last
Oh,
one.
okay. There you go. Does it make sense now?
Yes.
Okay. You still with me? All right, B. I like B. be required you to think, though. And so you may not have gotten it today, but I think you should get it if you see it on the exam. And you'll probably see something like this on the exam. Okay? Okay. B says identify a compound from the table that can be dissolved in water. So I'm going to take whatever compound I choose. I'm going to dissolve it in H2O. Okay? It can be dissolved in water to produce a basic solution. Okay? If I want it to be a basic solution, I need it to produce what? I need it to produce OH negative. Okay? Write the net ionic equation for the reaction that occurs to cause the solution to be basic. Okay? Now, do y'all remember in your notes when we would look at something and determine whether it was going to make a basic solution or an acidic solution? And I'll show you how we did it. All right. Remember, we said Li is the cation, I negative is the anion, right? So which one's going to form the base? Li, right? Because it's going to combine with LiOH, and I negative would make what? HI. LiOH is what kind of base? We'll review this. All right. A strong base is any element in group 1 or 2 bonded to hydroxide except magnesium and beryllium. Correct? Correct. I feel like I've harped on this for a really long time and we can't remember our strong bases. Okay? Let's go ahead and go over our strong acids right quick. What are our strong acids? HCl, HBr, HI, H2SO4, HNO3, HClO4. Okay? Those are our 6 strong acids. So, LiOH is a strong base. HI is a strong acid. So if I take a strong base and a strong acid, what's it going to give me? It's going to be neutral, right? That's going to be a neutral solution. So is that going to give me a basic solution? No. Can't use that one. Okay? KOH is a what? Strong base. HI is a strong acid. So therefore, if I mix them together, it's going to be neutral. Can't be that one. Okay? LiOH is a strong base. HF is a weak acid. What will this give me? Strong. It will give me a basic solution, right? So I could choose that one, or you could also choose NaF. It will give you the same thing, okay? Because NaOH is a strong base, HF is a weak acid, so this one would work as well. And they would have given you credit for using either one of them. So y'all choose, do we want to use LiF or NaF? I don't care. NaF. All right. So we're going to use NaF. So we're going to put NaF in H2O. Okay? Now, I'm going to erase this hydroxide real quick. So what is this going to give me? We already said it's going to give me NaOH plus HF, right? Everybody agree with me? Yes. Now, it told me that it wants me to write the net ionic equation. So what do I have to do? Decide who's going to dissociate and who's not, right? Anything bonded to sodium is what? Soluble. And pretty much almost all of your ionic bonds are soluble, okay? So this is going to go to Na positive plus F negative plus H2O. Goes back and forth to NaOH is a what? Strong base. So it dissociates into Na positive plus OH negative. HF is a weak acid, so it does not what? Dissociate. So then I cross out my spectator. Who's my spectator? Okay. So So we get F negative plus H2O goes back and forth to OH negative plus HF. And I get a point. And you would have also gotten a point for choosing one of the correct compounds. So that's worth 2. Okay. Now, shortcut. Do you remember how we said strong always wins and strong is always the what? Spectator. So if I take NaF plus H2O goes to NaOH plus HF, who's strong? NaOH. So Na and Na is my spectator. Okay? So F negative plus H2O goes to OH negative plus HF. That's why we say strong is the spectator. Does that make sense now? I should have explained that when we did that in class, why the strong was the spectator, and that would have helped. Mental note to self for next year. Okay. All right. We got that? We got that. Last one. All right. 7 is confusing. I ain't even gonna lie. We did this when we did the calorimetry lab, but the calculations with that calorimetry lab are a little bit ridiculous. So we're talking to our science and motion specialist about how we can make it make more sense, because it doesn't make sense to you when you do the lab, so therefore you don't get anything out of it. And this is where you should have gotten something out of it. Aluminum metal can be recycled from scrap metal by melting the metal to evaporate the impurities. A says calculate the amount of heat needed. So the amount of heat that I need to purify 1 mole of aluminum, originally at 298 Kelvin, by melting it. The melting point of aluminum is 933 Kelvin. The molar heat capacity of aluminum is 24 joules per mole Kelvin. And the heat of fusion, what does fusion mean? Yeah, we're trying to essentially evaporate it in this case. Is 10.7 kilojoules per mole. Okay? Now, I'm just going to go through this one because if I ask you questions, you're not going to get it. Okay? We all agree on that? We'll just go through this. All right. We did an equation where we have Q equals mCp delta T. We did that in your calorimetry lab. Okay? Where M is technically the mass, Cp is your heat capacity. Okay? There's the C, heat capacity. And delta T is the change in temperature, okay? In this case, I don't need the mass because I'm just trying to deal with moles, okay? So your mass in that case becomes moles. If they would have given this to me in grams, then I would have used that mass. Does that make sense? All right. So Q is your amount of heat, okay? So Q is your amount of heat. So how much heat how much heat is it going to take? First of all, before I can ever evaporate the impurities off, I've got it to do what? I've got to get it to melt, right? That's what it's telling me that I've got to do. I've got to get it to melt. So how much heat is it going to take to melt? Well, Q is equal to, what's my heat capacity here? 24 joules over moles per Kelvin. All right. Times how much temperature difference, what's my delta T going to be here? How am I going to find that? There you go. Do 933 minus 298. And we get 635 Kelvin. Okay? They said I only need to do 1 mole of this, so technically I would multiply it by 1. And if I needed to do 2 moles of it, then I would multiply it by 2. Do you understand where I'm going with this? Okay? So, my Kelvin cancels out, and if I go by the amount of sig figs I need, it's how many? 2, right? Because of this 24 right here. Okay. So I only need 2, so that would be 15,000 joules per mole. Okay. Notice they gave me my heat of fusion in kilojoules per mole, so I would probably change that to 15 kilojoules per mole. And they give you a point for just calculating how much energy it's going to take to heat it up. Okay? So that's how much it's going to take to heat it up. And then this is how much it's going to take to go through the heat of fusion process. So I add 10.7 there. And if I do the correct rounding with sig figs, I get 26 kilojoules per mole, plus another one. Okay. I'm okay on you not getting this one, okay? I really am. So don't stress over this one. I'm going to try to find another problem that works like this, and we'll do it again, just to kind of try to grasp it, okay? For those of you who feel like you need to get it. Hope. All right. All right, B. The equation for the overall process of extracting aluminum from aluminum oxide is shown below. Which requires less energy? Recycling existing aluminum, which we did up there, or extracting aluminum, which we're going to do down here from aluminum oxide. Justify your answer with a calculation. So in this case, they took solid aluminum oxide and got the aluminum out by doing this. Do we see that? Okay. They gave me a delta H. What does delta H tell me? Huh? It does, but in this case, that's not what I'm talking about. Delta H, enthalpy. Okay? Delta H is enthalpy, which gives me the total amount of what? Energy. Okay? So, this is the amount of energy it took to take aluminum oxide and change it to aluminum, right? Do we see that? Except this was how much energy it took to get how many moles of aluminum? 2. I want to get it down to how much energy it would take to make 1 so I can compare the two, right? Okay, so what do I need to do to this 1675? I need to divide it by 2. So 1675 kilojoules per mole divided by 2 would give me, I think, 837.5. And they would give you a point for that. So which one requires less energy? Recycling or extraction? Recycling. So you would say recycling requires less energy. And then they would give you 1 point for making the correct comparison. And that's it.